Welcome! This tutorial will showcase how to prepare toolpaths for CNC milling a smooth landscape model in alder wood. Generally, when milling in solid wood of different types, most settings are very similar, although the feed rate and the spindle speed may be adjusted depending on the hardness of the wood. Always make sure to check the reference table. If you go to any preferred web browser and you go to cnc.kthcnc.se, and if you go to the CAM software that we use, Fusion 360, and if you go to community feeds and speeds, where you have the reference datasheet, and then you can hold control and down, and here you can see that we have references for alder wood, and you can see the settings specific for this specific milling in this type of wood. Let's go back to Fusion 360 and upload our previously exported files. This may take a while, depending on the load on Autodesk servers. Fusion 360 is a cloud-based program. The files are hosted on Autodesk servers, so it might take a while to upload and process. Alright, when the files have been uploaded, you can double-click on the main 3D model document. And if you have polylines exported for engraving, you can already at this stage right mouse button and click on it and insert into current design. Wait for the process and then click OK to confirm. Very good. Now this document has been properly referenced in this document. Now you can change workspace from design to manufacture and create a new setup. First, make sure that the origin point is set properly to the point on the top of the stock where both the X and Y positive axes are tangential to the edges of your stock. In the second tab, Stock, make sure that the side offset is set to 0. The top offset of 1 mm compensates for any deviation from a perfectly horizontal surface, and for most circumstances 1 mm is a sufficient value. The bottom offset should be adjusted so that the stock height of the stock dimension is exactly what the physical stock material will have as thickness. So in this case we can add 0.6 mm, a very minuscule amount, but just to make sure that we can prepare a stock with dimensions of a length of 610, a width of 420 and a height of 61 mm. If your 3D model already has 5 mm at least of bottom margin, then you don't need to add any additional unless you want to even up the thickness of the physical stock. But if you have uploaded only a surface which does not accommodate for the bottom margin in itself, as in this solid, then you must make sure to add at least 5 mm of bottom offsets, so as not to rupture the holding of the vacuum of the stock during milling. Take note of these values. These values are what you will prepare the physical stock to. Click OK to confirm. Now, looking at the datasheet here, we find that the first toolpath that we intend to author is one with product ID 30 as a tool, and it's a 3D adaptive one. You can hold shift and scroll to go horizontally along the datasheet. So let's create a 3D adaptive clearing toolpath, and let's make sure that we select as tool in the previously imported tool library, product ID 30. This is a very wide tool, intended only for milling in wood, due to the fact that the wide diameter of the router bit creates a very high velocity of meeting with the material at the outer perimeter, which would be unsuitable for milling in plastic. We also see that it's a very short tool. It only has 37 mm from the tip of the tool to the collet of the tool holder. As such, we should add a restraint of no more than 36 mm of depth. We'll do that later. So we'll click select here. And then we see a representation of the tool here. And as for the spindle speed and the cutting feed rate, we'll go back to the datasheet and we'll see here. It is 4000 of RPM as spindle speed and 4000 as millimeter per minute for feed rate. So we can input as spindle speed 4000 RPM and as cutting feed rate 4000 millimeters per minute. It is a good procedure to only change the digits that you actually need to change and not delete the whole field, because the units are equally important. So just change the digits that you intend to change. It's also important here that you make positively sure to only change, if necessary, the spindle speed and never the ramp spindle speed, because this parameter, if changed, will be erroneously interpreted by the CNC machine and it will go amok, ramping up its feed rate instead until dashing into oblivion. So make sure to only change the spindle speed and the cutting feed rate here. If we check the datasheet and go to the right here by holding shift and scrolling, we see here that we have pull away enabled in the reference, and it's a good safety measure to have active. If we enable shaft and holder here and make sure that pull away is the chosen mode, pull away means that if the tool, the shaft of the tool or the collet of the tool holder would collide with unmilled material, then it would rather pull away than allowing that to happen. And we can increase the shaft clearance to 2 millimeters. In this case, the shaft is significantly smaller in diameter than the flutes of the actual cutter, but 2 millimeter shaft clearance is still standard procedure. We can go to the second tab, Geometry. Here we don't need a machining boundary for a free adaptive clearing toolpath. We should have rest machining active here. It means that succeeding toolpaths will take into account the volume of material that already has been milled away, so that it doesn't cover the same volume twice. In the third tab, Heights, there was one thing that we needed to change. The distance from the tip of the tool to the bottom of the collet was 37 millimeters, so we should make sure that the bottom height, the maximum allowed depth, is from the stock top with an offset of -36. That gives us 1 millimeter of leeway, and it's a restraint that increases the safety of the toolpath. If you at this stage don't remember the length of the tool from the tool holder, you can always go to Manage and Tool Library, and here you can see the tools that you actually have active for your documents, and we see that we have a length below holder of 37. So 36 is a prudent value. We'll go to Passes. Here it's important, since we are milling in wood, that we change the direction from climb to conventional. Very briefly put, conventional milling introduces an amount of rubbing between the flutes and the material to be cut. As such, it significantly reduces the expected durability of the tool that is used, but it also very significantly reduces vibrations or chattering when milling in a hard material such as solid wood. As such, we deem the lower expected durability of the tool a smaller price to be paid than the gain of reducing chattering, avoiding excessive micro vibrations for the machine. So conventional in solid wood it is. The maximum roughing step down should be set to 1.5 millimeters. As here in the datasheet, we have a maximum depth of cut, maximum individual pass depth of 1.5 millimeter. We should have no fine step down, and in Fusion 360, if you input as fine step down the same as the maximum roughing step down, that's the same as not having one at all. It will not introduce any intermediary steps between the maximum roughing step downs. You should disable flat tire detection. It increases the time it takes to generate toolpaths excessively, and it is of no use to us. As for the stock to leave, that is the material that is left unmilled for a succeeding toolpath to mill instead, thus actually defining the surface, instead of two toolpaths milling the same surface twice. As for the settings here, we can increase slightly the radial stock to leave to 1 millimeter, and since this is parametrically dependent, then it will change the axial stock to leave as well. You can overwrite this if you have any reason to, but 1 millimeter radially in the X and Y axes, and axially in the Z axis is good. And if we go to the datasheet, we see here that we have null millimeter, no fine step down, and we have no flat tire detection. And here it's important, for this specific tool, we need to change settings in the linking tab, which we usually don't change anything for the other tools. So we go to the fifth tab here, linking, and here there are 3 settings. The ramping angle should be set to 0.5. The helical ramp diameter should be set to 70, and the minimum ramp diameter should be set to 60. This makes sure that the tool, which actually has a stiff inset between sharp flutes, that it never does a too narrow helical move, which would leave unmilled material in the center. This makes sure that the helical ramps that I do always have a sufficient diameter, not to leave any unmilled material under the middle of the tool. With all of those parameters adjusted, then we can click OK to generate. This might take a while. And it is not uncommon for Fusion 360 to sort of jump back in the windows here. So just Alt-Tab back, and here we see it progressing. Very good. And it progresses as deep as it is allowed to go. We will follow up this toolpath with another that has a longer reach. Already at this stage, we can, purely for amusement, simulate the toolpath and then jump to the end of the toolpath. Make sure that you hide the toolpath and that you show the stock and that you change the colorization from operation to material. You can optionally also change the material to wall paint, which has less gloss than the default ceramic one. So here we see a representation of what is actually milled, or rather what is actually left after the first toolpath. And in the third tab, statistics, there is stated a machining time of 1 hour and 19 minutes or so. This simulated time will never be the actual milling time, and historically and statistically, different types of toolpaths have different deviation time factors. And if we open Rhino and Grasshopper, then we can open the Grasshopper definition where we can estimate the actual CNC toolpath times. If you go to your preferred web browser and go to gh as in grasshopper.kthcnc.se, it's only a URL to a Google Drive, and here you'll find in the definitions and in the fabrication subfolder and in the estimate CNC toolpath times, you'll find this very definition as well as an image preview of the definition. We'll go back to Rhino Grasshopper, and it was 1 hour and 19 minutes, and it was a 3D adaptive clearing toolpath. And we'll see that that singular toolpath takes approximately an estimated reasonable max time of 2 hours and 23 minutes. We should not exceed 6 hours of estimated toolpath time, and usually it's good procedure to aim to have at least half of the toolpath time for the actual toolpath that will define the surface. In this case, we will use 2 toolpaths to clear away material, and then the third toolpath should actually be the toolpath that defines the final surface. So we'll try to balance this. The easiest way to reduce the time it takes to mill a model is to reduce its size. You don't necessarily have to be that drastic, but if you reduce the size of the model with 50%, then you get 1/6 of the milling time. So even by reducing the size by a little can reduce the time it takes to mill by a relatively larger amount. Alright, we can go back to Fusion 360 and we can exit simulation. We want to follow up this 3D adaptive clearing toolpath with a very wide but fairly short tool with a longer tool. So we'll do another 3D adaptive clearing toolpath. We'll change the tool, and as for what tool, we can check the datasheet. So we'll go back here and then we'll move on to the next one, holding shift and scrolling to move sideways there. And here we see that we can use the product ID number 23. It was a 3D adaptive clearing toolpath, yes. So if we go to the library that we imported and we'll go down to 23, here we have it. It's longer, although still quite short. We have a length below holder from the tip of the tool to the bottom of the collets of the tool holder of 68 millimeters. If I recall correctly, the setup itself was 61 millimeter. That means that the thickness of the physical material that should be placed on the workbed is 61 millimeter, and as such 68 millimeter, or with a safety margin of 1 millimeter, 67 millimeter is more than enough to make sure that unmilled material will not be colliding with the tool holder. So we can click select here. And then as for the spindle speed and the cutting feed rate, we'll go back to the datasheet, and we have as spindle speed 6000 RPM. So we'll change 5 to 6. And as for the feed rate, we have 2500. So we'll change 1000 to 2500. We'll also activate shaft and holder and pull away and change 1 mm clearance of shaft to 2 mm. Now we can move on to the next tab, geometry. Here we should have no machining boundary, and we should also have rest machining active, which means that it does not mill away material that has been properly milled away by the previous one. And in the third tab, heights, we don't need to change anything, because from the stock top to the bottom it was 61 mm, and 68 mm of reach is more than enough. So we can go to the fourth tab, passes. Here it's equally important as for the previous one that we change the direction of the cut to conventional. And here it's very important that we change the maximum roughing step down to 3 millimeters. The depth of cut, together with the feed rate, the spindle speed, and the number of flutes, together defines the engagement load of the tool. This means that theoretically, if you decrease the roughing step down here, the depth of cut, you can increase the feed rate a little while maintaining the same spindle speed. But increasing the feed rate might increase also the rate of chipping of the material during milling, while going too deep or too slow through the material will significantly increase the heat that is generated during the engagement. So while one can experiment with these parameters, one should not be too aggressive. The fine step down here, the incremental steps in between the maximum roughing step downs, we can see in the reference what has been set here. In the comments here, we have no fine step down. So we are totally fine with only these step downs of 3 millimeters. Adding incremental step downs increases the time it takes to mill, of course, and this specific toolpath is only intended to clear away material. As such, it is not necessary to add these fine increments unless we find that the succeeding toolpath has too much material left to cut. Then it would reduce the load of the succeeding toolpath to also add finer increments here. Flat area detection should be disabled, and as for the stock to leave, here it's a little balance, because the massive diameter of the previous tool will have left a lot of radial margin, which means that if we leave this radial stock to leave as perhaps 1 millimeter, then this toolpath will reach into a lot of those remnants of radii that the previous tool left, but which poses no real problem for the succeeding toolpath to properly engage with. So it might be wise to increase the radial stock here to perhaps 4 mm, while overwriting the parametrically designated axial stock to leave and only leave 1 mm axially. This hopefully means that the effectiveness of this tool will be increased, because it will reduce the amount of time it dedicates to clearing away remnants of radii that the previous tool left, while it does not leave too much of a margin vertically or in the z-axis of the more horizontal surfaces that the next toolpath should engage with not too much load. And this tool does not need any specific changes for the linking settings, so we can simply click OK to generate this. And it jumped back. The window itself is just to Alt-Tab back. And as we see here, the generation of the toolpath is a relative success. It mills away material in those crevices that the larger diameter bit did not succeed in removing for the previous one, but it does not do so excessively, thanks to the settings we set for the radial stock to leave, while it properly engages with all of the surface that the previous toolpath was not able to engage with due to its lack of length. And we have here as an estimate 60 minutes of simulated time. We can go to simulate and see this as well. Yes, 60 minutes, and we can jump to the end of the toolpath. And here we see how the model should look at this stage. We can always toggle the visibility of the models to more properly see it, but this looks very promising. Let's input these 16 minutes into our Grasshopper definition. So we have 16 minutes as a free adaptive clearing toolpath, and that adds about half an hour. So as such, we have 2 hours and 52 minutes of expected max time for the first two toolpaths, whose purpose is only to clear away material. And this is good, because that leaves us more than half of the toolpath time to properly define the final surface. Let's go back to Fusion 360, and we can actually go to the datasheets, and then we'll see here what we have as our next toolpath. Our next toolpath will use router bit 18A as product ID, and it will be a 3D parallel toolpath. So we'll go back to Fusion, and we'll go to 3D and parallel, and we'll select another tool here, and we can go to our previously imported tool library, and we'll go to 18A. This is a very long tool. There is a drawback of using a long tool. A relatively longer tool will increase the deflection, the micro vibrations that the length of the tool and thus the reduced rigidity of the tool adds to the engagement. But it is still preferable to use a tool which has a sufficient length below holder, in this case 92 millimeters, with regards to the thickness of your material, which was 61 in our case. If one sees here a similar tool with a shorter length, which would add to an added rigidity and reduce chattering by a significant amount, we see that this has a length below holder of only 50 millimeter, which means that the top of the model is around here. And while this might not be unsuitable for certain circumstances, when you are learning to author toolpaths, it is better to be safe than sorry. So we'll choose this 18A and click select, and we'll go to the datasheet again, and we'll see here what do we have as for spindle speed and feed rate. We have 8000 RPM as spindle speed and 1500 as feed rate in millimeters per minute. So we can change the spindle speed to 8000 and the cutting feed rate to 1500. While the length of the tool itself will make sure that there is no collision between the tool holder and any unmilled material, the flute length, you see the yellow highlighted area here, is actually not very generous. So if there would be any very steep, I think that this would be non-critical, but if there would have been any significantly steeper area, high enough to pose a problem to this, then it's good to enable shaft and holder anyway. Make sure to change the mode from trimmed to pull away. And do use a 2 mm shaft clearance for safety's measure. Let's go to the second tab, the geometry. Here, as we're doing a 3D parallel now, it's important to set an adequate machining boundary. By default, it's a silhouette and the tool center on the boundary. It's beneficial to add an additional offset of a little less than the radius of the tool. So we have a diameter of 10, a radius of 5, and we should add an additional offset of 4 millimeters or so. This makes sure that the tool is properly allowed to define all of the surface area without being allowed to descend past the border. In the third tab, we don't need to change anything. 92 millimeters of distance from tip of the tool to bottom of tool holder or collet is more than sufficient. We can go to the fourth tab, passes. Here it's important, since we're milling in alder wood, a solid wood, and the fiber direction is along the x-axis, the long dimension of the stock material, that we change the direction to only other way. That is the same as conventional, and that gives a better final surface of the wood. The step over is by default set excessively low, less than 0.5 millimeter. We can begin at perhaps 3 millimeter, and then we'll see how long the toolpath will take with the step over set to 3 millimeters. And since the parallel toolpath is very linear in nature, we can very easily just adjust the step over so as to balance the time it takes to mill versus the cusps or ripples that is left in the material. Here you also see here that with a step over of 3 millimeter, the height of the cusps are a little less than 0.5 millimeter. Discernible to the eye, definitely, but not too difficult to sand away manually in post-processing. We don't want to have any stock to leave, so we can leave it unchecked. As for multi-axis, it is left at 3-axis, and as for linking, we don't change anything either. So we can go back to passes and click OK to generate. Alright, we can simulate this toolpath, and we can jump to the end of the toolpath, and we can temporarily hide the models. This is a very nice result. We can go to the third tab here, the statistics tab, and then we have here 1 hour and 4 minutes. We can go to our Grasshopper definition and add the third toolpath here, 1 hour and 4 minutes. This is not a 3D adaptive one, but a 3D parallel, and we're going a single way, only other way. That itself takes only 1 hour and 24 minutes, and that still leaves us 1 hour and 45 minutes as toolpath time. So let us, with these circumstances, make sure that we go back here, and we can exit simulation, and we double click on the icon here so as to enter the settings again, and we can change the step over from 3 millimeters to 1.5. This will leave a cusp height, instead of being a little less than 0.5 millimeter, of only slightly more than 1/10 of a millimeter. It should be noted here, if we temporarily show the model again, while adding perpendicular passes is advisable in XPS, when you have a material that has a grain direction, you always get the best surface when you go along the grain. So with solid wood, you have more to gain at reducing the step over than adding a perpendicular pass. Although, should you prefer to add a perpendicular pass, still make sure that the pass direction is along the grain in the first pass, since it's easier for the tool to cut along the grain. Alright, having reduced the step over to 1.5 millimeter, we can click OK. And we can Alt-Tab back into Fusion. Alright, and we see here that the simulated time is 2 hours and 7 minutes. We can input that immediately. 2 hours and 7 minutes. And as such, we have 5 hours and 37 minutes of expected reasonable max time for these 3 toolpaths. We have 2 toolpaths, 2 trace operations as well, but those generally take a very short amount of time. This is very reasonable. Let's go back to Fusion and let's also simulate this and see what sort of results we get. We can temporarily hide the models and we can jump to the end of the toolpath. And we see it progressing here. And you see that the cusps that are left are much less discernible, although they will always be most discernible when there's a high slope. This is absolutely great. Manually sanding the ripples away where they are most excessive will not be a problem during the post-processing stage. We can exit simulation. We can also show the models, and the last thing that we want to do is 2 trace operations to trace first the roads with a flat end mill, thus creating a inset or a groove with a rectangular profile, and then to subtly engrave with a V-shaped bit the property line here. So we check the datasheets, and here we have tool number 1 should be used, and it's a trace operation, a 2D trace operation. So we'll add a 2D trace, and we'll select tool number product ID 1, this one. Let's select it. Let's check the datasheet. We have 7,000 as spindle speed, 7,000 RPM, and we have 1,250 as feed rate. 1,250. The very low feed per tooth or ship load per tooth is to make sure that there is not excessive chipping when milling the wood with a flat end mill. As you see here, the 2D operations have less functionality, so we'll have to visually ourselves make sure that there are no collisions. This specific tool is very, very long, so this will not pose a problem. But it might be a problem for the other toolpath with a much shorter tool. Alright, this looks good, and then we'll go to the Geometry tab, and then selecting the curves is easy. If you have exported the curves in different layers, you can expand the models, you can expand your document file, you can expand the reference file that we previously right mouse button click and insert it into drawing, and then you can expand the sketches, and then you have the roads there, and you can simply select them as such. So now we have them there, very good. In heights, we don't have much to change, and we don't need to change anything. In passes, we'll need to make sure that the axial offset, right now it's simply following the surface. But if we do an axial offset of -1, then the inset of the rectangular groove will be 1 millimeter below the projected polyline on the landscape surface. Let's go back to the datasheet so as to make sure that we don't omit anything. We have an axial offset of 1 millimeter negative, we have no stroke to leave and no chamfer. Chamfer is an option that might appear for the 2D trace operation for certain curves, but not all. Click OK, and then we can hide the models, and we can go to Actions and Simulate, and we can jump to End of Toolpath, and we see here our simulated results. While not a perfect representation of the width of the road, it is still very clear what is happening here. Alright, this is expected to take 2 minutes, so we can exit simulation and input that here. So as for our fourth toolpath, we have 2 minutes, and it's a 2D operation. We have now a total of 5 hours and 39 minutes. And then we should add another 2D trace operation. Let's see here in the datasheet what tool, product ID we should use, number 27. So we'll select that and go down here, and then number 27. And as for the spindle speed and the cutting feed rate, we have 12,000 and 1,000. So 12,000 as spindle speed and 1,000 as cutting feed rate. As for the geometry, we should select the property line, and heights we don't need to change anything, and passes we should make sure that the axial offset here, since a 45-degree bit with a total of 90-degree angle, if you go down 1 millimeter axial offset, -1 millimeter, then you create a groove with 2 millimeters of width. So if we add here -0.3, that would lead to a width of the groove of 0.6 millimeters. We'll need to disable chamfer for this one as well. Alright, there is nothing to be changed in linking, so we can just click OK. And then we'll simulate this and go to End of Toolpath. And it is subtle, and it will be less subtle when the slope is greater. But as of now, with the shading, it is a little accentuated by the difference in hue. It will not be as accentuated in the actual milling. I think that it looks good. And we see that it takes 1 minute. So we'll add 1 minute here, and it might be not too important here, but we'll add 1 minute, and it's going to be a 2D operation. And we see that we have 5 hours and 40 minutes. Very reasonable as an estimated reasonable max time for 5 toolpaths. We'll go back to Fusion 360. Before moving on to the penultimate step of verifying collisions for the toolpaths, we also want to point out that the CNC machine has 6 tool holders and a very restricted amount of collets for specific shaft diameters. So while the tool library has been customized to show here the proper tool holder for each tool that is referenced, it is important to note that while it is entirely possible to use the very same tool for a multiple amount of toolpaths, if you use different tools, make sure that they do not take up the same tool holder. If you use a 10mm ball end mill, don't use a 10mm flat end mill, because those two 10mm router bits would require 2 collets of 10mm shaft diameter, which is something that we don't have. So make sure to be a little creative about what tools that you use, so as not to produce a scenario where different tools take up the same tool holder, thus not being able to be used for the same operation. Here, all of these 5 toolpaths uses 5 different tools with different tool holders, so everything is great. Now let's move on to the verification of collisions. Let's go to Actions and Simulate. Let's go to Info, and we have here 5 collisions. And to view these collisions, it's easiest either to click this blue View Issues there, but if this has disappeared, you can always find it, Information and Issues. And here we see that there's a collision between the stock and the shoulder. If we go back a little, and I'll reduce the speed of the playback and then start here. I think I see now that it's this very tiny amount of unmilled material that is milled here. So there's the collision, we saw it, and it was non-critical. It was very good that Fusion 360 registered it, but we saw it that it was such a tiny amount, it would not have proven a critical collision. One thing to take note of here also is that this specific router bit, it is specified in the tool library to have only 1.5 millimeters of sharp flute here, because as you see, it is here represented as a sort of cylinder with a sharp base and a stiff part over it. The representation is practical but not entirely valid, because this router bit has sharp flutes extending all the way up here. So this yellow area should actually be yellow all the way up here, but it has a part in the center here that is not covered by flutes at all. And that stiff part is approximately a little more than 1.5 millimeter above the tip of the tool. So this representation is made partly on the limitations of the tool library in Fusion 360, but mostly to put emphasis on the fact that this tool should not be used for ramping more than 1.5 millimeters at a time. So we can move forward to the next registered collision here, and it's in the same spot, or approximately the same spot. If we zoom in by scrolling with the mouse wheel here, and we go slightly before, I think that we can identify that it's that one there. Exactly. It's not a problem at all. This is so minuscule it's funny. Yes. And let's go to the third one. Here it was a little larger. Let's go, if we scroll out again and scroll in closer to where we are now, and then we can go a little before and wait for the mesh to generate here, and then we can play. Not a problem. Very good. Then we'll go to the fourth one, and we are in the same area that we were previously. And if we go a little before, I think that we should see, yes, here it is. No problem at all. Very good. And then the fifth and final is here. And we should scroll out and scroll in, and then go a little to before. And we are still in the collision, so to say. Let's see if we can move a little to the left. Yes, and here we have the culprits, and it's not going to be a problem at all. We can play. Great. All right. 1, 2, 3, 4, 5, 6. And the sixth one is in the same area as well. Yes, not a problem. It is a good thing that Fusion 360 registers these collisions, and you should visually verify all individual collisions. Close this now. Because even though most registered collisions are non-critical in nature, we don't want to miss any critical one. And they do appear. Seldom with the settings chosen here, but there might be situations when there are critical collisions registered, and then you will have to change the settings so as to avoid that. Alright, the first toolpath has been properly verified to have no critical collisions. Let's simulate this one. Let's go to the info tab here. We see the collisions here, no collisions. Very good. And then we'll go to the third tab here. We'll go to actions and simulates. And we'll go to info and we'll wait for the verification of collisions. No collisions. Very good. We can exit. Then the 2D operations are very important to visually verify the whole toolpath yourself. You can check if there are any registered collisions, but then you will also need to push play, choose an adequate playback speed, and with this tool it's not going to be a problem at all. Because the flute segment is very, very generous, and the length itself even more so, of course, and it was not a problem at all. So we can exit simulation, and then let's see if we do the same for this one. Here you see that this tool has a very, very, very short distance from the tip of the tool to the bottom of the tool holder or the collets. So when we push play here, we can reduce the speed. We still saw that there was not a collision there, and we are well above. We can increase the speed a little, the playback speed, so to say. Let's see here and reduce it here. Reduced, I said. Let's jump back here. I missed it. Yes, we are well above over here. And we see that the slope creates this extra wide growth there. It's more about the topography than the tool itself. And now when it goes down here, it's going to be important as well. Yes, but that proved no problem at all. That's great. Let's allow it to finish. That's great. So now we have verified that these 5 toolpaths are safe to run with no critical collisions registered, and also reasonable to run with regards to expected time to mill. What we should do now is to simply select. It is recommendable to select them one at a time. It is possible to create one combined toolpath with all of the toolpaths included, but since the CNC machine not very frequently and not too regularly, but perhaps once every 2 or 3 weeks, freezes up during operation, and we need to manually restart the toolpath or make a manual splitting of the toolpath, then it is advisable that you manually post-process each and one of them individually. So with the first one selected, you can go to Actions and Post-Process. And here, make sure to choose the post from the library that you imported previously. In this case, the MultiCAM KTH Alexander one for the large MultiCAM 3000 series. It is very important that you do not update these individual post-processes, because that would overwrite the custom changes made to a previous version with a generic later version. Just make sure to select it. And then make sure that the output folder is a folder where you know where to find these toolpaths. You can specify another by clicking the Select Output folder. The name of the toolpath should have a very strict syntax or format. This is because the CNC machine will only be able to read the toolpath files that has a name that does not include any special characters, any spaces, any periods, any punctuation symbols, and it also only shows the 1.5 dozen or so characters. It's quite a restricted interface. So make sure that you select the date that you have booked the CNC machine to mill on in big endian format. So 24/06/12 underscore and then 1 for the first toolpath of the operation, and then underscore the tool holder that is going to be used. So T3 in this case. With the date, the order of the toolpath, and the tool holder number. That is actually sufficient, but you can also add a suffix after this, perhaps Norrbyskogen, alder wood, only landscape smooth. Before you click post, make sure to select all of this with Ctrl A and copy this with Ctrl C. That makes it easier for you when you progress with the other ones. So now you can click post and wait for the prompt that it was successfully posted. Very good. Then you can move on to the next one. And you can post process. You can simply paste the previous one and then change the order from 1 to 2, the second toolpath, tool holder 1 in this case, and then keep the suffix as is and post, and successfully posted. And the third one, actions, post process, paste that, the third toolpath using tool holder 2 and post this. Very good. And then the fourth one, post process, the fourth toolpath and using tool holder 5 and post. And then the fifth, Ctrl V, and then the fifth and tool holder 6 and post. When all of your toolpaths are exported, you can go to where you have exported them, and then to make it easy to download these toolpaths and put them in the server folder on the computer that is connected to the CNC machine, it is advisable that you go to cnc.kthcnc.se, it's only a URL to a Google Drive, and then there is a folder called temporary storage. And if you enter here, you can create a new folder that is called your name, and then in that folder you can simply upload this. Having done so, we are done with the workflow, and you should focus on preparing the physical stock, matching the dimensions of the digital stock as defined in the setup in Fusion 360. You can always find that by double-clicking the icon by the left of the setup 1 here, and then go to stock, and here you see them. You can click cancel, and then while being done with the workflow, we can also simulate the whole setup, not to find collisions because we have already found those and verified those, but to go to the end of the toolpath of all of them. This will yield a more accurate representation of the simulated stock after the operation. And then you can right mouse click on the stock, and then go to stock and save stock, and you can save it with any name and in a directory that you find suitable. And then when you go there, you can simply click and drag into Rhino. Let's save this and open our previous CAM file here, and we can add here 02 alder wood smooth model, only landscape, 5 hours and 40 minutes of expected maximum milling time. And then we can simply click and drag this into here and import it, and using default settings. And when the import is done, it should be automatically selected. And then we can move this perhaps 600 millimeters to the right. and change the layer of this so that it's correct. And then if we go to the Architect display mode, we can see a more accurate representation that is possible in Fusion 360 as of how the simulated result of the operation will look like. Thank you for your time.